in this video we are going to talk about the concept of angular momentum, which is represented by the letter capital L. In this video we are going to see about the three things of angular momentum. First is basic definition, second is mathematical operation of angular momentum, third is angular momentum calculation about axis of rotation. So these three things we are going to see. So let us begin with the basic definition. The basic definition can be understood by relating translational motion with rotational motion. What happens in translational motion? We derived a physical quantity called linear momentum, which is defined as the quantity of linear motion body possesses during its motion. Similarly, in rotational motion we have the concept called angular momentum, whose basic definition can be quantity of rotational motion a body possesses during its rotational motion, then about a certain point. This point is very much of importance while understanding the concept of angular momentum, because if we change the point of observation, the quantity of rotational motion the body is having may change. So this is the basic definition, and we can say that linear momentum and angular momentum both are equivalent to each other in their respective domains. So for rotational motion we have angular momentum, for translational motion we have linear momentum. Both are giving us the quantity of motion present in the body, whether it is translating or rotating. So this is the basic definition. Here the certain point, the point of observation, again I am telling you, this is very important while calculating the angular momentum. That's why it is very much important. We will see it in the mathematical expression of it. So let us move on to the mathematical expression. Mathematical expression, to understand the mathematical expression, we take the basic definition of one of the basic definitions of angular momentum is moment of linear momentum. In physics, whenever we taking the moment of any physical quantities, we have to take the cross product of that physical quantity with the position vector. In this case, the physical quantity whose moment has to be taken is linear momentum. So the angular momentum is mathematically written at r cross p. Suppose this is a point of observation A, and about this point of observation at a certain distance a particle is moving with a certain velocity v and having the momentum p. So we draw the position vector from point A to the place of the particle and give it a name as r vector, and this is the linear momentum. So hence we can calculate the angular momentum as r cross p. And to get the direction of angular momentum, we mathematically will get the result in the form of I, j or k cap. This gives us the sense of the direction of angular momentum. But we can say that whatever the angular momentum is coming, whatever the angular momentum vector is coming, it is perpendicular to both r and p. So angular momentum vector is perpendicular to position vector and linear momentum vector, because the result we are getting from the cross product of r and p. And mathematically we know that whenever we take the cross product of two vectors, we will get the third vector which is perpendicular to both the vectors. So it is perpendicular to both r and p vector. And physically we can use some methods like right hand screw rule and other methods to find out the direction of angular momentum. Now, what is the connection of mathematical expression and physical definition, like quantity of motion, quantity of rotational motion, giving us the idea of angular momentum? how this mathematical expression r cross p is giving us the idea of quantity of rotational motion. We can understand the relation between quantity of rotational motion and L equal to r cross p by the help of a simple example. What we are going to do here is we take one example in which the particle is moving along the positive x-axis with a certain momentum, let us say p, and the point of observation we are taking it as A, which is present at the origin. Now we draw the position vector from this point of observation to the place of the particle having momentum p and give it a name as r. Here we can clearly see that r and p both are parallel, and in mathematics whenever we take the cross product of two parallel vectors will always come out to be 0. So in this case, when the point of observation is A, the angular momentum of this particle which is moving along the x-axis comes out to be 0. So how the quantity of rotational motion is also 0 here? If we place an observer here and he observes this point, this particle which is moving along x-axis, and he is sitting here, he will see the particle going along positive x-axis and will say that it is only having a linear motion. There is no rotational motion present in the body. So when there is no rotational motion present in the body, we can say that quantity of rotational motion is 0. So the observer point of view is that the rotational motion is 0, and the mathematical point of view of angular momentum is also giving us the result as 0. So we can connect both of them and say that the angular momentum gives us the idea of quantity of rotational motion present in the body. Now this gave us the idea how to calculate and how to interpret, how to understand the angular momentum. Next we take the case of calculation of angular momentum about a fixed point, about a rotational axis, about a rotational axis. We are going to calculate the angular momentum about a rotational axis, and whose rotational axis? A particle is rotating in a circle of radius r. So we draw the diagram here. Suppose particle is rotating like this in this circle present here, and the position of particle at a certain time is here, and the circular motion giving us the radius r, and this is the axis of rotation, and the angular velocity omega is a constant. Now we observe this particle angular momentum with two positions. One is at the center of the circular motion and other is just above the center of the circular motion at a certain distance, let us say y. So in both the cases we will calculate the angular momentum of this rotating particle about the fixed rotational axis, and will try to conclude some results. Now in both the cases, first case we will do it parallelly. Now in first case the particle position is here, and in second case particle position is also here. We take it as x-axis, we'll take it as y-axis, and we'll take it as z-axis. In this case also, this will give us the negative z-axis. Then particle is rotating like this, then its momentum must be along negative z-axis, and it is equal to mv. So in this case also the particle is moving along negative x direction and its momentum is mv. So what is the momentum value mv? If the particle is rotating with constant angular velocity omega with radius r, we can write it as v r omega, v as r omega, and giving it a direction in minus k cap direction. So p value is this. In this case 1, what is the position vector? Position vector is this. Position vector is this. Case 1, position vector is this. In case 2, position vector is changed because point of observation is changed. It is at P. In case 2, point of observation is changed, so position vector will change. Let us say it is r. So this magnitude was r, its magnitude here is also r, and this magnitude was y, which we have taken. In case 1, we are getting r vector along the positive x direction, so we can write it as ri cap. In second case, r vector we are getting in two sense. One sense is in negative y direction, another sense is in positive x direction. So y value is along negative y axis direction and r value is along positive x axis direction, so we can write it as position vector as r y minus j plus r I cap. So next we will calculate the angular momentum in both the cases, case 1 and case 2. So L equal to r cross p in first case, L equal to r cross p in second case. R is equal to r I cap in first case, p is equal to m r omega minus k cap. If we take the cross product n r and p, we will get m r square omega I, and k will give us minus j, and minus give us plus. So this is L, angular momentum in first case. M r square can be written as I, because if we take the moment of inertia of this mass m along this about this axis, it will come out as m r square. And second case, if we take the position vector, we have calculated as y minus j plus r I cap. So and p remains the same as m r omega minus k cap. We calculate angular momentum. Firstly, what we do cross product of both these two. M r omega y in magnitude will get, j k will give us I, j and cross k will give us I, and minus plus. So this will get first component. In case 2, second component r I cap and m r omega minus k cap, cross product will give us, so m r square omega I minus k will give us positive j. So this is the result for second case. Angular momentum m r omega remains the same y I cap, but m r square we can write it as I omega j cap. In both the cases we are getting the different results. Common term is I omega. So what we can conclude here? We can conclude one thing here. If we see the diagram, this is the first case, this is the second case. In first case, we are getting the angular momentum of this particle as L is equal to I omega j cap. And in second case, we are getting two components. One component is this, second component is this. When the point of observation was A, we are getting the angular momentum as this. In second case, when the point of observation was B, we are getting two components. One component I omega j cap in this direction, second component in this direction, whose value was equal to m r omega y I cap, m r omega y I cap. So we are getting the different results from the same axis of rotation if we are choosing the different points. So conclusion is that, so L about axis of rotation can be different if we are choosing different points of observation. We are choosing different points of observation. We are getting the different results of angular momentum. One is I omega j cap and two is this. The component of both the two will give us the net angular momentum in the case when the point of observation is B. Further, we